Morning. Let's see.
Morning.
I got it.
Good morning. I'm tired. I'm also tired.
Hey. You tired? It's weird. I can hear you over there, but not here. Okay. Huh. Why can't I hear you here? Stop, Ozzy. Here, I'm checking my audio. Can one of y'all say something? Anything? Can you hear me? Lily, can you hear me? No. Okay, that's bizarre because it should be. Okay, why is it doing that then?
Hi.
Mhm.
Hello.
Hey! I can hear you over there, but can you hear me?
You're very glitchy. You're very glitchy.
I know why. Okay. It's hearing, it's picking me up over there, not over here. Let me do this. There we go. Should be better. You hear me now?
Yeah, it's better.
There we go.
Yes, much.
Adjusting
much,
things.
much.
There we go. Good morning. Who came in? Hi, Sky. Who's that? Ella, Jules, somebody's head. Hey, Jules. How are you?
Good.
Good.
I'm not here because
Oh, Ella's sick too? Okay. So we have
got
Sky.
it from me, who got it from my mom,
Oh my
and
goodness.
who got it from the baby.
Oh
Who
no.
got it from, I don't know.
Whoever the baby visited. Yep. Oh my goodness. So I think this is going to be it then, except maybe Eleanor and Drew, wherever Drew is. Drew? Right here. Right here. All right, gang.
And more news, it's my birthday at the day after tomorrow.
All right. And how old will you be?
10.
That's what I thought.
First double digits.
Awesome. So Jules has a birthday coming up. Sky, you doing okay? Yeah?
Many people are sick.
Yeah, you know, it's definitely going around. It's the season for bugs, and I suspect we're gonna see even more.
Flu season.
Put all your stuff. Where's all your stuff? You put it somewhere. Yeah, Alec just mentioned giant spiders. So yeah,
Green
Jocelyn,
ones?
yeah, Jocelyn, you won't have them. Georgia has, oh, here comes Eleanor.
There's been a lot.
Georgia has a new species here that comes from Asia. It's called the spider, and they're huge. And they spin these amazing webs, these golden webs. They're yellow and black spiders.
Ours has like 5 layers. And
Yeah, it's a 3-layer web. They have
Ours
this
is like
orb, and then they
3.
have 2 others. Yep.
Ours is 5.
So, oh really? So I got, there was
ours,
one yesterday when I was at
Oh my
church.
gosh, I felt so bad because we had a whole load of them. We had a whole family.
Oh
It was
yeah?
like one by our window, and our window is pretty big. It's like big, like as big as that window.
Yeah, uh-huh.
And the spider web covered the whole entire thing.
Wow. So,
And, like,
so yeah, they look like, Jocelyn, since you don't get them, they look like that.
Oh.
Ah!
Yeah.
My mom would freak out. She hates spiders.
I think they're pretty, and it's interesting because they were, it
I
just
love
so
spiders. They're
happened
really cute.
that when I was at church yesterday, this particular spider was, it was like, the tree is, and there's a hill, so it was lower than most of them are. And with its perception, it was up pretty high, but I could actually stand close enough to it to get a good look. You gotta get your own pencil. I'm not. All right.
And
Have Ozzy fetch it. Like,
we
There you
have
go.
these like super colorful spiders.
So here's Eleanor. So
And-
that's everybody, unless
guess what?
Ella's gonna. Do you know if Ella's gonna tune in? Or is she not feeling well enough?
No,
Poor thing. I'm sorry to hear that.
she threw. So when me and my mom got it, we kind of got it at the same time.
Yeah.
So she got it first a little bit, and so that night she threw up twice, but like
Ew, hate that.
threw up, breathe in, threw up,
Ew.
breathe in, threw up, breathe in.
I'm eating dry cereal right now because I forgot about class.
You're fine,
And then
Eleanor.
I did 2 of those, and Ella did 4 of them.
Wow.
Ella threw up, breathe in, throw up, breathe in, throw up, breathe in, and like a lot more, like 7 times of that, 4 times.
Okay, well, let's get to, boys, let's get to class stuff. First off, let me hand out anything I have for you that is graded. Jules, would you take this to Ella, please? Eleanor, I'll get you next week. Lily, I'll get you next week. Oh gosh, they're stuck together and I can't lick my fingers. Ah, Sky, there you go. Sky 1.
Rico has his eye on what?
Well, look at what she did. I'm not even sure. What's the other thing? His eyes on everything.
Sharing is caring?
Yeah, I like that. It was great.
Is that the thing? Sharing is caring?
Be sure that your homework for this week, it goes in the folder up
Oh,
there.
I'm gonna be good at
Miss
sharing.
Danny,
Yes.
I was listening to Christmas music because the day before yesterday, I was listening to some music and then randomly just every song after that one song was Christmas.
Oh,
And so I started listening to Christmas music. And when I read it, I'm like, the Grinch.
oh, that's a great idea.
I don't know why. It just popped into my head.
Yep.
Danny, did you
All right, so we're gonna start this lesson. So what I did for this week is, you good?
What one is the?
So it's 9. We're on lesson 9. So this week I actually did your PowerPoint by weirdly enough, I made it look like your book pages. So because I figured some of you would be home. So if you have your book, does anybody have their book with them? You got your book?
Wait, is sharing is caring or what?
Sharing
no,
is
that's
caring is the one to
lesson
turn in this
You mean
week.
this one?
Lesson 9.
Oh,
Yeah.
this week? Okay.
Yeah.
I'm gonna start with.
Because I think it's what it was for 9.
Yes.
So this is the end of the quarter, guys. So that means progress reports will go out after this class. So whatever you have turned in that I can grade will get included. If you're still missing work, it's gonna show up that way on your progress reports. Well, then it depends. If it's missing long enough, it's 0.
No.
Okay, so here we go. Y'all can see that at home? You can see the screen?
Yes.
So we're talking today about covalent bonds and bonds in metal, okay? So here's exactly what your book looks like, but I left the blanks in here for us to fill in. And just so you guys know, Senya may join in, or we're not sure. She hurt her knee, so she was going to get it looked at this morning. Yeah, I know. She's been dancing. I hope she didn't hurt dancing. Well, I think she injured it.
Because I was sailing.
So we're going to stay on topic. All right, so when we talked about the little sticky-footed guy at the beginning, what was he? What kind of animal was that on the first page there?
A gecko.
Gecko. A gecko, they're so cute.
I guess.
Adorable.
It talks about the gecko's feet, right? And it talks about how they have these little tiny hairs that cover the pads of their feet, and that's how they can seemingly defy gravity and stick to stuff. And I've seen like high magnification of gecko feet, and it's really cool. So for the questions that came about that little bit, it says, why is it important that billions of spatulae come into contact with the surface the gecko is climbing? Who's got that? Does anybody here have their book? Nobody here. Drew, you should have your book. You live here. Where's your book?
It's
Go grab it.
upstairs.
Grab it. So it's because the spatulae come in contact with the surface. So there's more attractive forces between the gecko's feet and the surface. So if you've ever seen gecko feet, that's something to definitely look at, like high magnification pictures of gecko feet. It's fascinating. So what uses do you think you could find for an adhesive that works like a gecko's foot?
Tape,
Toys. Yeah. What else could you use it for?
glue.
Glue. It's kind of like Velcro. So-
Oh yeah.
Yeah.
You can use it for jackets.
Volcano like kit thing, and it was like an experiment.
Yeah.
Not really, but
For fixing broken things.
Uh-huh.
plastic. But you velcroed a volcano to it, filled it. a bath bomb in it
Uh-huh.
and filled it up with water, and the bath bomb
Oh,
would, like,
yeah.
explode.
Came out of it.
It'd be so
That's true. But it's talking about something like gecko feet, not actually like amputating gecko feet. So something similar.
You
So
can
how
use it to glue your principal to the wall.
There you go. That would be your mother in most cases. So how are
Actually, no, my father. My father is our
there you
principal.
go, the principal in covalent bonds. So it's talking about covalent bonds, and last week we talked about ionic bonds. Who can tell me the main difference between like a covalent bond and an ionic bond? Anybody know?
Question mark.
So in an ionic bond, if you remember, you've got two atoms that are actually ions. One of them is positively charged and one of them is negatively charged because one of them gained something and the other lost something. What are the somethings? Do you remember?
Life.
Gained an electron or lost an electron? Do you guys remember that? So if you've got atoms that gained or lost an electron, then they become ions, right? They're either positive or negatively charged. And in those cases, when the two ions come together, they make an ionic bond, and that is when one atom takes an electron from another atom. It's almost like it steals it. In a covalent bond, it's different because the atoms are sharing the valence electrons.
Sharing is caring.
Sharing is caring. So for ionic bonds, it's about stealing or taking. And covalent bonds are about sharing. That's the difference. So when you have an ionic bond, we don't call the compound a molecule. We call it a formula unit. Molecules are covalently bonded. So in our lab today, let's see, Jocelyn, did you do the lab yet for this one, or are you doing it later?
Last week.
I'm doing it later.
Okay, cool. So nobody's done it yet. Perfect. All right. So what we're doing today in lab is we are comparing an ionic compound and a covalent compound, and we are going to see how they, see how you can tell the difference between them by heating them. So ionic bonds, if you guys remember, are really strong.
I don't have lab 9.
You don't have 9? Yeah, it's because
No,
it's online. It's online.
Oh, okay.
Yeah, you have it. You can have it. Yeah, it's okay. There's nothing for you to do. You just have to watch it.
Okay.
So
I thought it was like an actual like hands-on lab. I'm like,
no, I gotta send out the next time.
I had lab 8. I don't have lab 9.
Yeah, no, you're good. So what we're gonna do is we're gonna heat two substances. Now the ionic substance we're gonna heat is sodium chloride. What is that?
I was just gonna say.
Salt. Good, Drew.
I looked at the lab on paper.
Okay, good. So the other substance that we're going to heat is the covalent substance, and that is sucrose. What is sucrose? Who knows what sucrose is?
Salt.
Nope, sodium chloride's the salt. Sucrose is sugar, table sugar.
Yeah.
So we're gonna heat table salt and table sugar, and you're gonna see the difference in the bond strength between the two. It takes a whole lot more energy to break those bonds up and break down salt into another substance. Plus, it also just takes a lot of energy to break the bonds between the formula units, between each NaCl. Salt, sugar is easy. Yep. Yep. Well, that simple syrup is about dissolving and creating a solution. We're not going to be creating a solution. So the attractions between the shared electrons and protons in the nucleus of each atom hold the atoms together in a covalent bond, and they form a molecule. All right, so your book gave you an example of a water molecule. And it talked about a water molecule, an oxygen molecule, and a nitrogen molecule. Okay, so I forgot to put my table up, but you guys have a table in your binder, right? You guys have a periodic table in your binder? You have one, it's in your binder. It's towards the front. Can you look for it? Look in your binder towards the front. In the resources, there's a periodic table. All right, so for water, for example. So you've got an oxygen, and then you've got 2 hydrogens. Okay.
Hydrogens win.
Yep. How many valence electrons does oxygen have? Can anybody find that for me? You see oxygen right here?
6.
Who said that? Jocelyn?
Jocelyn.
6.
Hello.
That girl. It does. It has 6. So we'll draw them. 1, 2, let's see, 3, 4, 5, 6. Okay?
Where is it?
Now,
That's the exact diagram.
and then
I
hydrogen,
can't find
It
it.
does not look like the exact diagram.
it's okay. He's got, we just need that answer. It should be right around, can you tell what page that's on? What page of the
On
resources?
The very last page before the.
The last page of the preface
Yeah.
before, so you're too far this way. You gotta come back this way.
Dog.
And it's before this.
What page are we on in our book?
So we're on 140. So how many valence electrons does hydrogen have? That's, it's got 1. It's number 1, right?
1.
So if we draw the hydrogen, let's do hydrogen this way.
A new laptop.
I'll make the hydrogen red. Let's put him here. And we'll put him here. Okay, so hydrogen has 1. So what happens here when you bond these 2 atoms, whoops, ding ding, covalently?
What the heck?
How many valence electrons does oxygen want to be happy? What's our rule? What's the number? Octet rule. How many electrons are we looking for? 8. Yes, good. Okay, so how many do we have?
6. We need
1, 2, 3, 4, 5, 6. Whoops, 6. Sorry. And then 7 and 8. Right?
I thought that was 2 for.
So how many does hydrogen want to be happy? It can't have 8.
Hydrogen wants 7.
It wants 2.
No.
Because 2 is the first one. Remember, 1 has 2, 2 has 2. So here we go. He wants 2, and look, he's got 2, right? And then the oxygen has 8, and you end up with a covalent molecule. And there's a reason why oxygen is shaped this way. Oxygen is actually shaped this way. It kind of, some people think of it like Mickey Mouse. It is kind of shaped like that. And the reason that it's shaped that way has to, has to do with the type of bond that you have there. Now, when we look at oxygen, let's stop, I keep bumping that thing. Here's oxygen again.
What is it?
It's in my bin over here. So
Oh,
we said oxygen had 6, right? Can we say oxygen had 6?
Yeah.
Okay. 1, 2, 3, 4, 5, 6. And how many? 1, 2, 3, 4, 5, 6. So what ends up happening here is they sort of switch around. And if you draw it nicely, you get this. So how many do we have here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We're all there. So now, because we have 6 and 6, right? There's all 12. But look how many we have. 1, 2, 1, 2. You see that? So we're gonna call this a double bond. And we're gonna call this, what do you suppose?
Oh, no, that's a double.
This one's a single, okay? Because in this
Oh,
case,
sorry.
yeah, I didn't draw it very well, did I? Yeah. This one's a
it
single
looks like a
bond.
bunch of eyeballs.
Because it's only one, this is pairs. So it's pairs we're concerned with. How many pairs do we have? 1, 2 pairs. This, we only have 1 pair. See? 1 pair, 1 pair. So we're gonna call this a single bond. And we're gonna call this one a double bond.
No, now we're going to show circle.
Okay, now, how about nitrogen? Somebody tell me, how many electrons does a nitrogen have?
Electron.
What are valence electrons?
5.
5. Okay, so here's a nitrogen. And here's another nitrogen. Okay, so we have 5. So the way nitrogen is gonna work is it's gonna do 1, 2, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And then we're gonna have what kind of bond? A triple bond. And remember, it's about pairs, not electrons, pairs of electrons. So basically count your electrons and divide by 2, right? It's pairs that matter. So we have these 3 types of bonds that your book talked about. Then we also have bonds that have to do with a charge. So at the bottom of page 140, it asks you, now I know that atoms in a covalent bond are held together by, and that would be the attractions between the shared electrons and protons in each atom's nucleus. All right. So molecular compounds are not good conductors. Think about sugar and salt always. If you put, remember that ionic compounds were only good conductors in a solution, right? So remember last week we took a little pile of salt, you coming? A little pile of salt, and it didn't do anything when we tried to send electricity through it, right? But when we dissolved the salt in the water, what happened? What happened when we dissolved the salt in the water and we tried to run the, come here, Ozzy. We tried to run a stream of electricity through it with that Christmas light. What happened?
It exploded.
It did not explode. It lit up.
I wasn't there.
It conducted. So it conducted electricity because ionic compounds have these charges, right? Ions have charges. Are you trying to come in my lap? Just staring at me. So covalent compounds are not good, are not good conductors, whether or not they're in a solution. So if you had sugar solution, could you conduct electricity through that? No, it wouldn't do anything. Sorry, he's so spoiled.
Sorry, I have cats everywhere. I have this giant cat right here.
Willie and the cats.
And then I have Hermione who is crawling behind me.
Mm-hmm.
This
Ooh,
is
you have
looks like a dog.
Yup. So wires such as the ones found in your headphones are insulated with rubber or plastic, your book says, and that is, it's asked about what other things are insulated, and it gave examples of cords for chargers and everything.
I have some examples. Just
What do you have? What examples did you have?
Other examples would be like extension cords or lamp cords
Yes.
or chargers. They're all insulated so you don't get electrocuted or the wire short circuit and then you just break your charger.
Amen. Excellent.
But if they didn't have like the plastic or something over it, you would be wasting like probably half your money on more chargers every day because you're accidentally short circuiting.
You'd be getting shocked all the time.
Sit
All right,
together.
we look on 142. On page 142, you guys have a chart. Do you see that? Drew, do you see
Chart.
that?
Yes, chart. I have chart.
Chart. It talks about melting points of molecular and ionic compounds. And this is going to be kind of what happens in lab today. So your graph should look something like this based on the information you've been given. And if you look which of those, so they have isopropyl alcohol, octane, sodium chloride, and water. All right, and the only ionic compound listed there is sodium chloride. And you look at its boiling point and look at that. 1,465 degrees Celsius. Yeah,
What is salt?
that is the boiling point. Yeah, boiling point of salt. So those ionic bonds are really, really strong, and they're very hard to break.
Are we using Celsius and not Kelvin?
You don't use Kelvin very often, only for certain things.
Miss Danny,
Yes,
is it raining where you live?
not today, but it rained all weekend. It rained really bad. It was some of the strongest rain we've had in a long time. People
This is what it looks like here.
The beach now.
There you go. Oh, I saw you guys have a beach. Yeah, Alex's entire backyard flooded. It was kind of.
You have tree.
We had a mini flash flood in our basement because a pipe burst.
All we need to
Yeah.
do is take a few trees down.
Oh no, that's not good.
Lot
Alright,
of stuff, so including our Christmas tree box.
So it says, now I know that the properties of molecular compounds include low melting points, the inability to conduct electric current when melted or dissolved in water. Now, when we start talking about partially charged atoms, here's where we get into the concepts of polar and non-polar, okay? Now, basically what you're dealing with here is unequal sharing of electrons. So they're still sharing, right? But they're not sharing them equally. kind of like if you and your friend had, 3 cookies and you're sharing the cookies. Somebody's not going to take all 3 cookies, but maybe one of you gets 1 and the other one of you gets 2, right? That's what I mean by,
Or you just split the last cookie in half so you each have an equal amount.
you could do that, but you can't split an electron yet. So unequal sharing of electrons, unequal sharing of electrons causes covalently bonded atoms to have slight electric charges. So if the sharing of electrons is equal, what do we call that kind of a bond?
Polar.
Non-polar. Good guess. Yep. So non-polar means it's equally shared. So think about a magnet. Remember, a magnet has 2 poles, right? A positive pole and a negative pole. So if they cancel each other out perfectly, then it's non-polar. It's not right. Yeah. But if you have a little more charge on one side, then we're going to have what we call a polar bond. Now, here's an interesting thing. So water is actually a polar molecule. And do you guys know what a surfactant is?
What?
So a surfactant, this is interesting. So soap, dish soap is a surfactant. And when you put
chemical?
Yeah, well, so basically what it's going to do is when you put your water molecules in the sink with an oily dish, all right, and then you dump your dish soap in, what it does is it causes it's almost like tiny magnets. Now we're making tiny magnets, and it's allowing the water to pull the oil off of the dishes. So the picture here at the bottom says hydrogen forms a nonpolar bond with another hydrogen. In hydrogen fluoride, fluorine attracts electrons more strongly than hydrogen does. And a polar bond is more, oh, hang on, come here. Jason's leaving for the first trip. I love you. For the first trip since February.
Usually not very good to try to make
Be
a bond
safe.
with 2 different
Wear your mask, I love you.
elements.
He usually travels a lot. Yeah, is Drew chop liver? He usually travels all the time, and his last trip was actually February 13th. So this is his first.
My dad, for his work, sometimes he'll have to travel places for work.
Yep, he travels a lot, so he's going to Colorado.
My dad might not be here for my birthday.
Aw.
Which I'm really sad.
Aw.
He's like, I'll give you a kiss.
Oh, that's sweet.
I'm like,
There was one year where my dad wasn't there for my birthday. I was very sad.
Because under round 1, it's hydrogen and hydrogen. It's true. So you should open your book to 143. So under round 1, it has hydrogen and hydrogen, which is H2. So it says, imagine that you're a sportscaster. Write a commentary describing each of the tug-of-war matchups below. So if you look, you got your hydrogen and hydrogen, and they're the same. So they're going to have the same amount of charge. So for example, it says, this one's a draw. The 2 hydrogens are pulling equally on the electrons. But if you look at the picture at the bottom, that fluorine says, I want it more. It's not pulling equally, it's pulling harder. So it says fluorine wins. It has the stronger pull on the electrons, leaving hydrogen with a slightly positive charge. Bye. So now we go
wait,
here.
is it this?
That's today's lesson, yeah. That's today. I was
Is
looking
that
at
what
the
we're supposed to be on?
I was looking in your book, but yeah, we're gonna look at that too. So hang on to that, don't lose your spot. So polar bonds and molecules, and it shows you your water molecule, and it shows you how it's bent. See, it's at that bent shape. It looks like Mickey Mouse or a teddy bear. And then it says at the bottom, it talks about the Dead Sea. And so the Dead Sea has so much salt in the water that just about anything will float in it. I actually have a bucket upstairs of Dead Sea salt for like the bathtub. It's nice stuff. So the Dead Sea is a saltwater lake in the Middle East. It is so salty that neither fish nor plants can survive in it. The water contains many dissolved compounds, including sodium chloride, magnesium chloride, and potassium chloride. So what is an example of, we say water is an example of a molecular compound. And it says what kind of bond forms when, this type of bond forms when two nonmetals share electrons. That would be molecular, okay? And properties of these include low melting point and boiling point and the inability to conduct current. And then it talks on the next page about your sodium chloride. So water is a molecular compound. Was sodium chloride ionic or molecular? Do you remember? That one was ionic. That was what we did last week. We're doing it again today.
I didn't do that.
So
last week.
ionic is, so here's the thing. Molecular is two nonmetals. Ionic is a metal and a nonmetal. Okay? Every time. That will help you a lot with remembering them. And they have high melting points and they can conduct current when they're dissolved in water. So if you look on page 145, Drew, you got page 145? If you look on 145, it has an assess your understanding. So what type of bonds are formed when atoms share electrons unequally? What do you have there?
How do you share electrons unequally?
Well, that's what we were just saying. Sometimes there's more of a charge towards one side or the other. Wait, what is it? Covalent polar bond. Right. Covalent polar. Covalent because they're sharing. Polar because they're not sharing equally. So would carbon dioxide or water have a higher boiling point? What do you think? What do you think, Lily? Are you waving an answer at me or are you just
Isn't carbon dioxide a gas?
Carbon dioxide,
carbon dioxide? Okay, why do you think?
because on this carbon dioxide, it has more power over it.
It has more power over it. On the where are you looking? On this? So you're looking over here on wait. You looking at this part? Where were you looking?
Right there, yeah.
Okay, where do we see carbon dioxide? Water? Where do we see it? I don't see it there. Well, let me ask you this. A boiling point means that a substance is changing from what state of matter to what state of matter? From a boiling, from a liquid to a gas. So how do we typically see water? As a liquid. And how do we typically see carbon dioxide? As a gas. So that means that carbon dioxide is going to have a really low boiling point. And it says water is the answer because attractions between polar water molecules require more energy to overcome than attractions between non-polar carbon dioxide molecules. So the easiest molecules to break apart would be what? Polar covalent, right? So how can bonding determine the properties of a substance? Who's got an answer for that one? How can bonding determine the properties of a
You
substance?
can match the boiling points and the melting places with what you already have.
Right, melting point, boiling point, what else? So in general, we talked about our ionic compounds. They have high melting point, high boiling point. They're brittle. When they're dissolved in water, they can conduct electric current. And then we talked about our covalent compounds, and those are low boiling point, low melting point. They tend to be somewhat stretchy. The bonds are stretchy. If you break a big salt crystal, it's going to break in a nice clean line because it's all bonded in this perfect little lattice. It's like breaking a Lego apart. But if you break certain molecular compounds apart, they're not going to separate that way. It's almost like pulling on Play-Doh.
Speaking of Legos, I got this huge Lego set. It's an amusement park.
Is it Friends or Lego? Like old school Lego?
Like Lego Friends.
Okay,
It's like almost like as big
I'll
as
have to
half
show
this
you our
table.
Legos.
As big as half this table.
We have a lot of Legos. I'll have to show
I have
you.
at least
It comes with the full.
I have like 10 million sets, and I have so many Legos that me and my sister can make like 3 houses and 2 hospitals.
Some
I've actually done that before.
covalent become slightly negative or slightly positive when they pull more or less strongly on shared electrons. So then we talked about, after we talked about our covalent bonds, we talked about bonds in metals. So there are 3 main types of chemical bonds. There's ionic, covalent, and metallic. There's also hydrogen, but we're not going to talk too much about that this year. We're going to talk about ionic bonds, covalent bonds, and metallic bonds. Okay, now metallic bonds are different in that metals make this nice, neat little lattice, but the electrons kind of float all around the way that they link up together. So they sometimes refer to it as a sea of electrons. And that is why metal is a good conductor, because of the free floating electrons, electrical charge can just hop right through, right? So it talks about superconductors on page 146. And it says in 1911, physicist Heike Kamerlingh Onus made a remarkable discovery when he cooled mercury to negative 269 Celsius, which is 4 Kelvin. The mercury no longer resisted the flow of electric current. The cool mercury became the world's first superconductor. A superconductor is a material that has no resistance to the flow of electric current. Certain metals and alloys become superconductors as they are cooled to very low temperatures. This means they can carry electric current for a long period of time without losing energy as heat. Superconductors can also be used to produce very powerful magnetic fields. These magnetic fields can be used to levitate and move high-speed trains. So this train is a maglev. I was going to ask when you were there. Yep, so we did it too when we were in China. There's a maglev train in China that Alec has been on, Drew and Cole and I have been on. Yeah, it's really crazy because it goes nuts fast. We're talking insane fast because it actually levitates above the track. It uses magnet, the repelling of the magnets.
Magnets. I'm gonna become an inventor when I grow up, and I have my first invention. I just haven't built it yet because it's called the hover car, and it's basically the car that hovers above the ground.
Brilliant.
Yes, so how would you make it hover? You would have to have these really special roads that would cost millions of dollars per 100.
Or she could, or
called reverse magnets.
Reverse magnets. There you go. So it would be like the maglev train, very similar, but more like individual passenger. That's a great idea. Hang on, we're gonna go back to
and it's gonna be like a flat car, so you lay down in it.
Oh, cool.
That will be billions of dollars.
Well, maybe not. You never know.
But
We'll talk back.
I'll
back
make
to it
billions
later.
of dollars.
There she will. There she will. Alec, hang on. We're gonna come back. We're gonna come back to the lesson. So write your answers to each question. So it asks, how is a superconductor different from a regular conductor? Superconductors have no what? No resistance. Good job, Drew. Resistance is kind of like, say you're trying to pass 300 gallons of water through a tube every 3 minutes, but your tube is this big around versus your tube is this big around. So you can have more resistance versus less resistance. That's the idea. And they don't lose any energy as heat. You know, when when wires run electricity, sometimes you can feel the heat from them. So a superconductor wouldn't lose that energy as heat. So power lines lose 10 to 15% of the electric current they carry as heat. So why might scientists want to create superconducting power lines? Yeah, definitely makes it more efficient. And it would save money and everything else. So we start talking about metal here. It says, what is the structure of a metal crystal? So a metal crystal is composed of closely packed, positively charged metal ions. The valence electrons drift among the ions. So that's what I was talking about, having that electron sea. So they really do just kind of float around in there. And there was a picture of that in your homework. So nonmetals are unlikely to have the type of bonding shown here because valence electrons are strongly held by atoms of nonmetals. But with metals, those valence electrons just float around like in a sea. So it says at the bottom of 147, I'm watching our time because we've got to start lab shortly. It says, now I know that a metal crystal consists of closely packed, positively charged metal ions with valence electrons, bless you, drifting among the ions. And it gives you this great picture of this really fun motorcycle and points out all the different elements of metallic bonding. So metallic bonding explains many of the common physical properties of metals. Properties of metals include shiny, that's called luster, right? High levels of malleability. What's malleability?
Flexible, kind of.
You can hammer it in, yeah, you can hammer it into a different shape. Ductility, what's ductility?
It can be
Ductility is about drawing it into a wire. Can it be drawn out into a thin wire? Yes. And thermal conductivity. So what's
it can
thermal conductivity?
Conducts heat.
And
Dang
what's,
it.
hang on, you answer this one, Jules. What's electrical conductivity?
It can
I asked Jules, what was it?
it can
Conduct electricity. You got it. Good girl. Excellent. So metals act this way because positive metal ions are attracted to the loose electrons all around rather than the metal ions. So it talks about here how the fender is malleable and how it has metal fins cool the motorcycle by conducting heat. You've seen it. So let's look here at this last page before we head off to lab. Metals conduct electric current easily because the valence electrons in a metal can move freely among the atoms. So it wants you to draw some arrows to examples here. So thermal conductivity, it showed you a pan, right? Electrical conductivity, it showed you a cord. And then in ductility, it pointed out both paper clips and the cord, right? And then malleability, it shows you the pan and the, what is that? Does anybody know what that is? What's that?
It is a tuba.
The French horn. French horn.
Okay.
It also shows luster. Sorry, I'm choking. So then it says, name an example of a metal object that shows both luster and malleability. Who has an example? Luster and malleability.
Gold.
Gold? That gold what? A gold something.
A gold bar.
A gold bar or a gold coin? Sure. Yep. They
I have
stamp out coins, right?
I have a coin that's like worth $20.
Wow. What other hang on. What other objects do you think contain steel? It talks about buildings with steel beams and bridges and all that. Okay, then it gets down to this point at the bottom about this bit with the shark. And it goes back for the whole chapter and it wants to know what accounts for the properties of metals. Who can tell me that? Why are metals shiny, have luster, conduct electricity, are malleable and ductile?
Because God wanted them to be.
It's because of the way their valence electrons can move and the way that they're bonded. It all comes down to how they're bonded. Why are metals good conductors of electric current? Who's got that one? 151. Why are metals good conductors of electric current? What about those electrons? Wait, you tell me, Jules, you got it.
Takes a long time for them to melt.
No, because all those free-flowing electrons in the structure of a bunch of metal atoms all bonded together, right? And it talks about how the electrons just flow around freely. All right, and then the properties of metals include what? Oh wait, non-metal spoon would not conduct thermal energy to your hand, right? That's why you can use a wooden spoon when you're stirring a pot. So what are the properties of metals? They are malleable, ductile, luster, good conductors of thermal and electrical energy. There you go. I think we got all of them. All right, so looking at your homework real fast. I mean, not your homework, your notes. If you guys turn to the pages in your binder with your notes, I'm gonna go over those answers with you real quick before lab. We only have about a minute, so you can go back and catch the lesson. So circle all the covalent bonds. Do you have it up? Turn to the page that says covalent bonds at the top. See? Got it. Circle all of the covalent bonds in the electron dot diagrams. So you should circle those ones in the middle. We drew up there in the middle. And then which bonds are double bonds? So that is the O2, the oxygen. which is a triple bond, the nitrogen, NN. Do you see that, Drew? You're on the right page. And which molecules have, can't see. Go this way, look. Right here. You're on number 4. Which molecules have polar bonds?
Hydrogen, fluoride.
Yes, good girl. And then compare and contrast oxygen and fluorine. To compare them, we'd say they're both nonpolar and oxygen has a double bond, but fluorine has a single bond, right? Great. What letter do we get for number 6? Who's got it?
B.
And good. How about 7? E, very good. How about 8?
D.
D, very good. How about 9?
C.
C, good job. And 10?
A.
A, you're so fast. All right. And what do points A and B represent on the next page? Bonding in metals. What do A and B represent? Flip that page, Drew. Here we go.
Malleability and C. Wait, am I reading?
So A is representing the positive metal ion. B is representing the moving valence electron. And then what's C? You know what C is and what's going on in this picture? What's happening is it's showing malleability, right? Showing that the metal is being mushed on one side. You see that?
Yeah.
And then for C, what it shows is that this force of whacking it or squishing it or whatever we just did has moved some of the positive ions, but the attraction to the electrons keeping the metal from breaking, right? It's not breaking, it's bending. All right, what do we have for number 4? Who's got 4? Drew, you have number 4?
C.
Good. How about you, Drew? What's 5?
5 is
E. Sky, what you got for 6? You know that one yet? Oh, I can go to Alec. Alec, what do you have for 6?
C.
A.
Wait, no, 6?
C, D, A. Who's got, we're under building metals. Bonding in metals, sorry.
7 is E.
7 is E. Good. So it's C, D, A, E, and B. All right.
C what?
C, D, A, E, B.
Oh, okay.
Metallic bond.
And I just didn't.
That's okay. Metallic bond is an attraction between a positive metal ion and the electron surrounding. And an alloy is a mixture of 2 or more elements, at least one of which is a metal. Now, this slideshow is under the class participation. You should be able to see it in Teacher Ease, and of course, we'll put the video up there. We're gonna go do lab now. Now, for everybody who isn't here, who's typically here, like Eleanor and Lily, you guys go watch the lab. You can see the link through the Teacher Ease assignment for the lab. And something special at the end of this lab is I give you a recipe, a fun recipe that you may want to try that actually relates to the lab. Well, we'll do it here. So you guys are off to do that. And we're gonna go. Lily, were you gonna say something? You were looking at it. No, okay. All right, you guys. So we'll see you next week. Hopefully everybody feels better.
Bye.
Bye.
All right, let's